So am I audible? Type your registration numbers. So today we are going to see the important topic and very basic thing in machine learning is called as regression. I have introduced to you this concept in previous classes. Thing is, suppose I say y is equal to f of x, where this f is some function and it acts on the given input. Say this is my input and it produces some output. Okay, this function f is known, then you can easily find out this value y. Okay, so this kind of prediction is called as regression. Given any value of x, if you are able to find out the value of y, then this is something like an estimation. So regression, so what is regression? Is a task of approximating a mapping function f from input variable x to the continuous output, say y. So you can have this relation, as I said earlier, say y is equal to f of x. The output variable y is a real valued integer or float. So y can be integer or float. It can be some number, maybe say like 2.3, 2.5, any kind of such number is the actual value. Example, y may be some house price. Okay, so y may be some house price in say rupees, say 15 lakhs, 14 lakhs, whatever it is. So this is the outcome y. So input is some, suppose x can be you can say area of house and y can be cost of the house. Okay, so given some area, you must be able to find out the cost of the house. So this is a kind of a prediction. A regression problem requires the prediction of a quantity. Regression can have real valued or discrete input variable. So x can be anything, output is continuous. Okay, that is the problem domain. A problem with multiple input variables is often called as multivariate regression problem. For example, suppose y is a function of say some x1, x2 up to xn. Instead of only one variable, there is a list of variables. If this is the situation, then it is multivariate regression. Okay, output is one, but you have many inputs. So input, say output depends on many inputs. A regression problem where input variables are ordered by time, then it is called as time series forecasting. Okay, so if there is a timestamp of the input, say I want output for first time instance, then it may be y1 is equal to f of 1, say x1 you can say, then y2 is f of say x2, where 2 indicates now second time instant. Okay, so this suffix is now indicating the time. So if this is the case, then it is the time series regression problem. Okay. The skill of the model must be reported as an error in these predictions. So when you design some regressor, how do you evaluate that regressor? How it is, you can say, performing? What is the performance measure of this regressor? So it is evaluated mostly by a simple method called as root mean squared error method. So root mean squared error method, RMSE, is a measure of this error. So in general, suppose I say this is E is error, then I just say if say y is my actual value and y hat is the predicted value. So difference between them, and if I square it, okay, if this is the case, then it is root, and I should do it for all available data values. Say I is equal to suppose 1 to n, and I write here suffix I. So yi is now indicating, so if I is equal to 1, then first output, and it is its prediction. So when you have a training data set, it will be provided like this. Say this is my table of training. So I will value here and corresponding yi value. Suppose this is my so when I say x1, it is talking about this first element. When I say x2, it is talking about the second element. When I say y1, it is talking about the first entry in y table. So like that, these are known to me before I do the modeling. This will help me in designing a model, and how to check how much estimation, correct estimation is given by my model. I will do this check. So I will give my model a chance to predict. So I will give input as xi, and I will get the prediction yi. So this is actually model. So this f indicates a model now. Now when I supply actual x from this table, it will predict now some value yi, and the difference between the actual and the predicted value and its square, if I add for all these samples in the table, it will give me an error. Okay, and this theoretically should be 0. My model should be such that it should do the predictions as close to the original as possible.
Sir, your bottom side writing is not visible.
Yes?
Your bottom side writing is not visible to us.
Okay, okay. Just 1 minute. Is it visible now?
Yes, sir.
Okay. Now the best example of this regression is the most simple one, is called as linear regression, and fitting a straight line is the most simple problem in case of a regression problem. Now suppose I have one variable called as x here, and there is the dependent variable y. Independent variable x is the input, and dependent variable y is some output. Okay, as we have seen, it is f of x, y is equal to f of x. Okay, now suppose I have some training samples spread like this, and I want to fit a straight line. I want to approximate this relation between y and x given to me in this form using a straight line. So maybe this is the straight line which I can fit through this data such that error is minimum. Which error? The root mean square error is minimum. That means I am fitting a line such that the predicted value y and the actual value of y, they are very close to each other. I have to fit this line such that this error is minimized. For example, suppose I take this sample. So this is my first sample x1, and the corresponding value for x1 is this y1. So this is a true value of this point. This point you can plot if you know x1 and y1. But you see, I am fitting a straight line here. So this difference, this extra difference is appearing for y. So when I put x1, this line will give me output here. So this is my y1 predicted. So the difference between these two is this area. So error lies here. So this is my error. So y minus, say, y1 minus y1 predicted. Okay, if I do squaring of this, I will get a number, squared number. And I have to do this for all samples given as a training samples to me. For every samples here, I have to do this process. I have to find out the error. Okay, and suppose I put line over here. Instead of here, I suppose take a case, I am fitting line here. Now in that case, you will see that my error is too much. So this much of error I am adding. Okay, so this much. So this is a big gap. So this should not happen. I should fit lines such that for every sample, the line fitted is the best one. Okay, such that overall error in my system is minimized. So this is a simple concept used for fitting a straight line. Now there are types of regression models. The regression models can be broadly divided into two categories. A single feature based model, that is y is a function of x. Okay, so x is here one dimension. There is only one feature available to me. Say like relation between two variables, say y is here and x is here, and x is suppose area of house and y is cost of the house. Okay, so this is one feature, that is area is only considered and y cost is predicted. So this is a simple model, and there are two types in simple model, that is the linear relation. I assume that y and x are in relation and they are having a straight line kind of a relation, linear relation. There is another option, is that the relation is non-linear. Okay, so if relation is linear, that means I can write y equal to mx plus c kind of a thing. Okay, if I am able to fit a straight line, then relation between y and x is like this. If relation is not straight line, maybe a non-linear thing, then y may be some, let us say, beta 0 plus some beta 1 x1, maybe beta 1 x1 square, beta 2 x1 square, maybe so on. So this is also possible. So you can assume as per your data a proper model. So that is a challenge, which thing you will use. Okay, so this is about one dimension. When case is one dimension, you have this kind of options. When you have two dimensions or more dimensions and you produce some output y, in that case your y is a function of many variables. So x1, x2, x3, and maybe up to xn. Multiple, say, inputs, and you are producing single output. Here also you can assume that your relation between all these variables and output y is linear, or it may be non-linear. So you have four types in general. Input is one dimension, input is two or more dimension. So here input is two or more dimension. Then you have 1D feature, you can say, and relation is non-linear and linear. You have multiple features, your relation is linear or non-linear. So a problem is called regression problem when output variable is, so we have seen this, many different models can be used. The simplest is linear regression. It tries to fit the best hyperplane. Okay, so when you go to many dimensions, instead of calling a plane, you call it as hyperplane. So plane and hyperplane, it's a matter of just dimension. So when you say 3D case, you say plane. When it is more than 3 dimension, you say hyperplane. Now you have to respond to these questions. Let us see how many of you can understand this. Which of the following is a regression problem? So predicting age of a person, is this a regression problem or something else, or a classification problem? What do you think? Predicting age?
Regression problem.
Right. So when I predict the nationality of a person, is it a regression or a classification?
Classification.
Right. So predicting whether stock price of company will increase tomorrow?
Regression.
Think. See my question. My question is whether predicting that is stock price will increase tomorrow or not. So answer is either yes
Classification.
or no. Okay. So when answer is in this form, binary form, it is a classification problem. Now instead of that, if I ask predict stock price of a company for tomorrow, then it becomes regression problem. Okay. So there is a difference between these two. So predicting whether a document is related to history, simply it is a classification problem. So if you see these problems, see these questions carefully, if answer is of type yes, no, or answer is of type say class, which class, then that means you have a fixed kind of output, binary or maybe some integer numbers, fixed numbers of the class labels, not numbers actually, I should say class labels. Then it is a classification problem. What is the regression problem? Where you estimate a value, you predict a value. Okay, here you predict a class. Okay, so that thing you keep in mind. So here we will deal with estimation of a value. Now the simplest one is ordinary least square regression. So you will implement this in your practical maybe next week. So this is the most simple kind of problem, that is also with only one dimension. So minimize square areas of differences to minimize error. So what is the problem here is I have only 3 points, say 1, 2, 3, and my target is to fit this line such that squared error are minimized. Now what is concept of squaring error, or what exactly happens when I do square? Now see, if I fit a straight line for these 3 points like this, then this is my error. So if I square this error, then it is like this area. Okay. So if I square this difference, it becomes this area. If I square this difference, then it becomes like this. Okay. If I square this difference, it becomes like this. Now I have to fit the line such that the sum of the areas of these 3 boxes, sum of the areas of these 3 boxes is minimum. Okay. So for example, I have say this fitting, and suppose I change the line position like this. Points are same. You can see that these point positions are not changed. They are same. My target is to fit line. So I have just tilted this line somehow in this direction, and I fit this new line. Now see, possibly this area is slightly increased, but this has gone down, and this is almost same. Okay, so maybe overall error, that is area of these squares, is less. So instead of choosing this line, better is to choose this line. Okay, so we have to think about or we have to imagine about a situation where suppose I have to fit a straight line for 50 samples or 100 samples. So that time maybe this kind of visualization is not required, but if you build a concept based on this and design some algorithm which will take care of this, then you can easily solve or find out the best line for your data. Now, finding out this line equation, that means say y is equal to, suppose instead of using mx plus c kind of thing, now I am using a new variable beta and beta 0 and beta 1. Suppose I write this line equation in this form. Mind you, this is same as y equal to mx plus c. I am just rewriting in this form. So these are two things and they are same. Okay. So now my target is to find out beta 0 and beta 1 such that error is minimum. Okay. So this has to happen automatically. I'm not going to adjust the things by visualizing all the areas like this. Okay, so how do I do it? So we have a system of equations like this. Suppose I have a pair of samples, say x1 and y1. So actual value is x1 input and corresponding output is y1. Now what I do is I do prediction based on the line that I have assumed. So the line I have assumed gives me a predicted value yi is equal to beta 0 plus beta 1 xi. Suppose I is equal to 1, then I am talking about y1 predicted value and input is x1. Okay, so this combination of beta 0 plus beta 1 xi gives me a predicted value yi. So this is yi. And what is this small e1? It is talking about the difference. So that difference, as I said, say if this is the point x1 and this is corresponding true value of that particular input, and say this is my this is my straight line with equation, say y predicted is equal to beta 0 plus beta 1 x I. Okay, so I should say x only here. And this is your line. So when I put x1 into this equation, it predicts y1 cap. The predicted value is this much, and this much error is happening due to the position of this line. If my line is passing through this point, then there is no error because it will predict perfectly. Okay, but since my position of the line is here, my prediction is here. So that much error is in my estimation, and that is indicated over here by E1. Okay, so if I take now second sample Y2, then I am talking about X2 comma Y2. So X2 comma Y2, and for Y2, that is actual value Y2 is equal to this estimated value of Y2 plus the corresponding error. So I can keep on writing for all the available training samples like this, and I can write all these equations. So E1 to En, they are errors, corresponding errors for the predictions. Okay, what are now beta 0, beta 1? I am just repeating what is beta 0 and beta 1. Beta 0 and beta 1, they are these parameters of the line. Okay, y predicted value is equal to beta 0 plus beta 1 xi. Now target is to obtain beta 0, beta 1 such that error is minimum. So that we have to achieve. So before I do that, I just write all these equations in vector form. Now you have to just check whether I am writing with proper dimension. So this y, that is the collection of now all y values during my training. So this y is a collection of all these y's available in training set. Okay, so this collection of all y's will be this y. So what is dimension of this? There are n rows and 1 column. Okay, now this is equal to, so I take now this first row and multiply with this column. So what will be outcome? So it will be beta 0 plus beta 1 x1. So what is this? This is y1 predicted. Okay, so if you see the previous equation, it is talking about this. This is y1 predicted. Okay, and this is my error. So this E is now a vector. This E is now a vector which is just collection of all errors like this. Okay, so what is beta 0, beta 1? These are all, these two things are line parameters. So if I multiply now second row with this same column, then it will be y1 2 estimated equal to beta 0 plus beta 1 x2. Just multiply this row with this column. So like that, if you multiply all these rows with this column, then you will land to your previous set of equations. So that is what we want. So what is dimension of this? Dimension of this is n by 2. Okay, n by 2, because n is number of samples. So each row here is representing the corresponding sample x value. 2 means here there are 2 elements. Okay, so this is a very nice, you can say, arrangement in terms of a matrix and column multiplication to write all the equation in one go. So here this beta 0 into say beta 0 and beta 1, they are placed in a column. So it is 2 rows, 1 column. So if you multiply, it will be this product will be n by 1, and this error is also n by 1. So they will be added to give you y, which is also n by 1. So dimensions are matching. So in short, I can write this in just one line. So y is all the predictions collected, all the y's which is collected and placed in one column is equal to this matrix A. This one is called matrix A multiplied by this beta vector. This is beta vector added with error vector. So I can call this as error vector. This is beta vector. This is A matrix which has this construction. Okay, so keep this in mind. It will come to you again maybe in next derivation. So error, I am interested in error. So what I do, I just swap these variables. So error is now defined as y minus a into beta. So error is equal to y, capital Y. So remember, whenever I write a capital letter, it stands for matrix or a vector. Okay. So whenever I write small y, it stands for a single variable. Okay. So whenever I write capital Y, that means this thing is now a vector, because I know this is n by 1. So minus y cap. So this a into beta is predictions, all the predictions for given input x. Okay. Now we want to minimize the square of the error. So this is my error vector. I take square of this. So that is norm square. I want this quantity to be minimized. So I just write the individual error square and I add all of them. So as per our definition, this will be error square. Okay, so this will be error square, addition of that. Now we want to find out what is value of beta 0 and beta 1. So we want to minimize this error such that, minimize this squared error such that with the help of beta 0 and beta 1, so that my line is fit in proper way. So the tuning parameters which are available to me are beta 0 and beta 1. So they are my controlling knobs. I can play with this beta 0, I can play with this beta 1, and then I can check what is square of the error. But I have to do such a way that I have to change these values such that this factor becomes minimum. So we are now going to use the differentiation. to do this. So this is very simple. So I can formulate my problem like this: minimize this squared error, with respect to two variables. So what I am going to do is I am going to write the corresponding, say, values here. So this y and this a into beta, I know what is that. So I just write here, instead of in this form of norm square, I just write in the form of summation. Okay, so this yi is the actual value of given I, that is output. Xi is, so that means I am talking about this xi and yi. Beta 0, these are beta 0 and beta 1, these are line parameters. So this part is the predicted value and this is the actual value. So that is difference square. So it is same thing. I have done nothing. Okay, so it is just rewriting the same concept. Now to minimize this with respect to beta 0, I just differentiate this and equate to 0. So you can see here this equation I am differentiating with respect to beta 0. So if I differentiate, 2 will come out here and this will be yi. So I hope that you are noting down this derivation. This is important. You may not find full steps in book and book may be jumping here and there. They may write in one step. So hope you are writing this. So yi minus beta 0 plus beta 1 xi into minus of 1. Because of this minus 1, this will appear. So if I simplify this, this will be my simplification. I can bring this summation inside. I will bring this summation inside. Now see what happens if I bring that inside. You have to check your signs also. Be careful about this minus. Now see what I am doing is, for this particular term, I am writing this term where y bar is the mean value. Y bar is the mean value. That means, what is y bar? Y bar is representing mean, which is nothing but summation of all y's. So this will be I equal to 1 to n, summation of all y's divided by m. That is simple average or mean. So this I am calling it as y bar. So if I bring this n to the right hand side, so this same y I summation, I can write this as n into y bar. Okay, so this n into y bar, this I am substituting here for this particular summation yi. So this is same like this. Okay, then when I go inside, I check for this. It is just addition of beta 0 n times. This is addition of beta 0 n times. I am writing n into beta 0. Then I go inside, I check for this. Beta 1 is a constant. I can bring this out. And this is just summation of, this will be summation of I equal to 1 to n of xi. So again I can write this as n into x bar, because x bar is now representing the mean or average. Okay, so this becomes now simplified. So this is now y bar minus beta 0. So n I can throw out. So beta 0 minus beta 1 x bar. So we are interested in beta 0 here. So I write beta 0 is equal to y bar minus beta 1 into x bar. Okay. So this is how we compute beta 0, but still this beta 1 is unknown. Now we will take the second derivative. Now we will differentiate with respect to beta 1. Same error function. Now we are differentiating with respect to beta 1. So here you will find that xi will come into picture when I differentiate that equation with respect to beta 1. Now next step, I know what is value of beta 0 in terms of beta 1. So I put this beta 0 that we have calculated just now is beta 0 is equal to y bar minus beta 1 into x bar. So if I put that, so this is my modified equation. Here I am substituting this thing. So if I simplify further, this will be the next step. Okay, I take this xi out and I bring this beta 1 into all these things here. Now this becomes my beta 1. Okay. So it is beta 1. If you see carefully, it is I equal to 1 to n. Obviously, I equal to 1 to n here also. So yi, that is the outcome for ith sample, minus its mean value multiplied by its input. Okay. So this I have to do for all the samples from I equal to 1 to n divided by the input value xi minus the mean of that input multiplied by input. I have to do this summation for I equal to 1 to n. So if I do this division, I directly come up with value of beta which is best suited for my problem. So this is with the help of this equation, I directly land to beta 1 which is based on minimum squared error. And then I take this beta 1 and substitute here in this equation. I put this beta 1 value which is already calculated. I know mean value of x, I know mean value of y, and then I got corresponding beta 0. So I can easily find out beta 0, beta 1. So we will take a problem and program next class tomorrow. Okay, so we will stop here. Any doubt you can ask? Shall I stop?